Visual analytic tools combine the complementary strengths of humans and machines in human-in-the-loop systems. Machines provide quick computations and unbiased information processing, while humans provide invaluable domain expertise and sense-making capabilities. However, little consideration has yet been given to the ways inherent human biases might shape the visual analytic process. We propose that cognitive biases influence users' exploration of data in ways that are measurable through their interactions. We thus present 6 preliminary metrics that can be used to systematically detect and quantify bias from user interactions and demonstrate how the metrics might be used in an existing visual analytics system. Our proposed metrics can ultimately be used by visual analytics systems to mitigate the negative effects of cognitive biases by making users aware of bias processes throughout their analyses. Our metrics are computed based on the notions of coverage and distribution. We use the term coverage to mean roughly the amount of data exploration that a user has made on a dataset. Distribution, on the other hand, goes beyond how much of the data has been explored. Distribution metrics compare the dispersion of the user's interactions to a baseline model of unbiased behavior. Each of these ideas, coverage and distribution, are computed with respect to data points, attributes, and attribute weights. The precise descriptions and computations for the 6 metrics can be seen in the paper. We dedicate the remainder of this video to demonstrating what each of the metrics looks like as a user interacts with a visual analytics system. Interaxis is an exploratory visual analytics system that allows users to steer scatterplot axes by interacting directly with data points. Dragging points into either bin along the axis prompts the system to compute a new attribute weight vector that describes the difference between the two sets of points. For this video, we use a dataset of cars. The bias metrics have been integrated with Interaxis in the bar chart on the right. The width of each bar encodes the value of the given metric. Hovering on the bars for the data point metrics changes the radius of the circles in the scatterplot so that the data points that have been interacted with are made larger and the data points that have not been interacted with are made smaller. The attribute and attribute weight metrics are computed for each attribute of the data. The size of the metric bar reflects the maximum metric value across all attributes. Hovering over the metric bars changes the opacity of the bars along the axes. The attributes along which the user is more biased are given higher opacity, while the attributes along which the user is relatively unbiased are given lower opacity. The data point coverage metric is a measure of the proportion of data items that the user has interacted with that are unique. Interacting repeatedly with the same data will increase the bias level. Interacting with more unique data will lower the bias level. The data point distribution metric compares the distribution of the user's interactions across all of the data points to a baseline uniform distribution. If the user interacts with the data relatively evenly, the metric value will be low. However, if they continue to interact with a particular sports car, for example, the metric value will increase. The attribute coverage metric computes a metric value for each attribute in the data. It measures how much of the range of possible values for each attribute has been covered by the user's interactions. For example, if the user only interacts with cars with horsepower greater than 300, their interactions will not have covered the full range of values for that attribute, and thus the bias along that dimension will be high. The attribute distribution metric compares the user's interactions with the data for each attribute to the distribution of that attribute in the full dataset. For example, if 10% of the dataset of cars are sports cars, but 50% of interactions are with sports cars, this metric would detect a bias along that dimension. The attribute weight metrics are similar to the attribute metrics. There is a metric value computed for each attribute in the data, but here it considers the weight in the range of -1 to +1 that is applied to each attribute of the data throughout the user's exploration. Now consider the following usage scenario. Suppose Dorothy wants to use Interaxis to explore potential cars to buy. She drags cars she likes to the high end of the axis and cars she doesn't like to the low end of the axis. As she interacts with the system, the bias metrics are computed and the bars on the right are updated. Hovering on the data point coverage metric bar shows that Dorothy has explored the cars on the extreme ends of the x-axis, but not much in between. Curious what she has ignored, Dorothy hovers over several cars in between, noticing many compact and crossover SUVs. Dorothy had subconsciously dismissed all SUVs since she was interested in higher fuel economy cars. However, she likes Jeep Wranglers and Ford Escapes and decides to go test drive. In this case, the awareness of her cognitive process provided by the bias metrics allowed her to locate cars of greater interest to her. To see the precise computations for the metrics, as well as a more detailed case study describing their use, please see our paper.